So it's great to be here to talk about some more recent research that explores the intersection of efficient machine learning, or ML, and hardware accelerators. Actually, in my mind, this is probably one of the most exciting times to work on hardware specialization. So first of all, the demand is pretty strong, right? So there's actually a wide array of applications that require efficient acceleration in a very energy efficient way. So this is especially true for many of the machine learning workload. This is where some of these traditional general purpose devices are not going to be up to the task. Also, there's actually, with this cloud FPGAs and also this open source hardware, right, becoming widely available and also more usable. So it's probably more affordable right now to start a new project, right, building this different kind of new hardware accelerators. So really the cost is also lower. So with this in mind, it's actually not too surprising, right, to see the industry has started this sort of an arms race, right, on building the this efficient specialized ML processors for different market segments. To some extent, all the big tech companies are in this game, right, and so are many startup companies. This is also a hyperactive research area for academia. But if you look at many of these academic conferences, we often see this disconnect between the, let's say, the ML algorithm community and also the hardware community, right? So if you look at many of the ML conferences, so most of the papers focus on building new models on the commodity hardware, like GPUs, right? But if you look at the hardware community, right? If you look at for example, computer hardware conferences, so most of the papers are mainly working on the off-the-shelf, right, the existing models. So, but with both algorithms and also the hardware getting more specialized, we really think that there's a strong need to co-optimize or co-design the ML hardware, right? And also this specialization, we believe, will drive new design methodologies and also tools, so that we can build this new hardware architecture in a more efficient and also more agile way. Okay, so my talk today will be focusing on two topics. I'm going to talk about both design and design automation. So for each topic, I'm going to delve into one or two recent papers from our group. Okay, I'm going to start with the design aspect, where we look at hardware efficient DNN or deep learning algorithms. So I'm going to specifically talk about channel gating and precision gating. So we have published quite a few papers recently in both ML conferences and also computer architecture conference. So this is a joint work with the Cornell student Wei Zhe, Yichi Yuan, Richie, who recently graduated, and also my colleagues, Chris Sa and also Edward Sa. Later, I'll talk about automation side as well, where we talk about the programming and compilation for ML hardware. Okay, so let me start with the first topic. So actually, my group has been looking at efficient deep learning models for a while. We've been looking at different kinds of model pruning techniques. So if you look at the existing methods, we can roughly categorize them into a few classes. One is quantization. The other one is the sparse connection. Third one is the structural weights. So for quantization, my group is actually one of the first to build a hardware accelerator for binarized neural net. Also, we are among the first to look at the accurate method to do post-training data-free quantization. And for sparse connection, this is where we are looking at, right? So we are trying to remove the non-useful weights or connections or activations, right? So from the neural net, so we can do it either in a fine-grained manner or coarse-grained manner. Okay, so if you do it in a coarse-grained manner, one of the more popular technique is this like a group convolution, right? Like MobileNet, ShuffleNet. So they are the good examples, right? And the other interesting direction is where people try to enforce some structures in the weight matrix or weight tensors. Right? So one of the interesting work is this so-called one interesting direction is this so-called circular matrix, right? So basically where people are using this circular matrix for the weights. There are actually quite a few papers in both, again, ML conferences, also hardware conferences covering this topic. So we are actually last year, we published a paper at CVPR, so pointing out that there's a fundamental connection between the group convolution and the circular matrix. So we can actually unify them in the same framework called the unitary transform. Okay, if you're interested, you can check out this paper. But today, I actually want to talk more about another topic. So to some extent, most of the existing techniques, they are focusing on static optimization, static pruning. I'm going to talk about what do I mean by that. But today, I'll focus more on this a new technique called dynamic pruning. So more specifically, I'm going to be talking about fine-grained dynamic pruning. I'll talk about two methods. One is called channel gating, the other one is called precision gating. I'm going to start with the first one. Okay, I'll later on briefly introduce the second one. Okay, so before I introduce channel gating, let me just first briefly summarize, also give you a quick review of some of the classic static pruning techniques. Okay, so this is my DNN, right? So let's say we focus on convolution neural net, CNN, right? This is one Conv layer. So over here on the left, we have the input channels, right? So these are output channels, and these ones are the weight filters. So with a fine-grained sparse pruning, this is where we try to remove the individual weights or activations, right? In this case, we are trying to remove the weights, right? So this is where we can actually remove many of the weights from the filters. Okay? So nice thing about the fine-grained prunings is usually we can get pretty high accuracy and then get very high compression ratio. But one of the downsides is that it actually makes the model less structured, which is usually causing some trouble for hardware parallelization, especially for load balancing. We also need to have a special storage format as well. Another way to prune the network is using a more structural way called group convolution or grouped convolution. Okay. So in this case, again, using the same diagram. Right? So over here, we are grouping the output channels into two groups, right? The blue group and the green group. So same over here. So the input channels are also grouped. Okay. So with this grouping, the output group, the blue group, the blue output will only depends on the input from this blue input groups. Okay. Same thing for the green output, right? We'll only look at the green input channels. So by doing this, we automatically get a 2x reduction, right? In terms of the model size, right? We don't really need these weight filters anymore, right? And this weight matrix look more or less like this looks like a block diagonal matrix. Right? So this is a lot more structured. But with actually, just want to point out that one of the popular techniques called depth-wise Conv, right? Using mobile nets, it's just an extreme case, right? So where we have a diagonal matrix, right? In these weight filters. So one of the nice thing about these group convolutions, again, this is fairly structured, fairly regular, right? It's easier to implement, right? But the downside is usually, since we are doing this grouping, right? So there's actually less cross-channel, cross-input channel learning with such compression. So this is where we usually see a non-trivial loss of accuracy. So there are some workaround. Right? So one of the workaround is proposed in ShuffleNet, right? So where the idea is to shuffle the grouping, right, for the output layer, okay, before we connect it to the next layer. So these will actually facilitate more learning, more information flow across different channels. So ShuffleNet indeed turns out to be pretty effective in terms of regaining some accuracy. Okay, so these again, this is just a quick recap of some of the well-known techniques. The reason I call this static pruning is because if you look at all of these techniques, regardless how you prune the model, right? So whether you do it in a fine-grained way or coarse-grained way. Okay? So when you actually run the model at the inference time, so the amount of time, the number of cycles it takes, is going to remain the same, right? Regardless of how you prune the model. Right? So regardless of whether you're dealing with some sort of easy image or more difficult image. Hopefully this makes sense. Okay, so basically the inference time of the prune model is agnostic to the actual input. So that's why we call it static pruning, because the runtimes are not going to change dynamically at the inference time. But this is probably not how if you look at human, right? So this is probably not how our visual system works, right? At least for me, In many cases, for some of the easy images, I can immediately tell what's going on, right? In a split second. But for some of the more difficult images, it may take me a while to recognize, right, the object, right, in the image. So basically, our response sort of depends on the actual input, right, which is pretty natural. But how do we enable such behavior, right, in this DNN processor? So this is the research question that we are asking. Okay. All right, so here's the main idea behind channel gating. Right, so first let's look at CNNs. Here's the high-level idea. So again, we want to enable this sort of a dynamic behavior, right? So we want to spend less effort on this sort of easy images. So the idea here is that given input, right, we first want to run per pixel. So let's say per pixel for each output feature map, we want to run this partial layer compute. I'm going to give you a more concrete idea later on. So what do I mean by partial layer compute? But basically, first spend part of the effort, okay? And then we run it through a learn gate function. This is why it's called channel gating. We run through a learn gate function to determine whether this output pixel is important or not. Okay? If it's not important, then we are done. We're going to just leave with the partial result, the partial sum. Otherwise, we complete the rest of the compute, okay, for the important pixels. So eventually, we combine them. Okay? So this is the main idea, right? Again, this is dynamic, right? Because we are actually trying to exploit input-dependent properties. So for different input images, we may run different amount of compute for each pixel. And also this is refined grading, right? So we are really looking at this at the pixel level for the output feature map. Okay. And also really the key idea here is that for the unimportant ones, right, like this, we are going to use this partial result to approximate the final sum. So this is really the key idea. But of course, you may ask, right, is it a good idea or not, right, to do such approximation? So let me just show you some sort of some motivation, right? Also, this is actually we look at CIFAR-10, we look at ResNet model, we look at all the training samples, and we look at all layers, and we actually try to collect some statistics to justify whether this is a good idea or not. So first of all, by default, right? So we are using, again, for each convolution layer, right? So we are using 100% of the input channels, right? And all the weight filters to produce a final output. We call this as the final sum, right? What we are trying to measure is what if we just use a subset of the input channels and see how well the partial sum correlates with the final sum using the Pearson factor. Of course, right, in this case, by default, the correlation is 1, right? We haven't done anything yet. So what we did is we actually first tried, so what if we just use 50% of the input channels, okay? And of course, we don't need, we only also just need the 50% of the weight filters. So it turns out that the partial sum strongly correlates with the final sum. So this is pretty good news, right? So this means that we can probably infer something useful, right? Even from this partial result, even if we just use a small subset of input channels. And we actually try to go even further. So we try to go down to 25%. Okay? And turns out that the correlation is still pretty strong, right? About 0.7, which is again good news. We can go even lower. We can go down to 1/8 or 12.5% of input channels. And it turns out that we still have some modest correlation. Okay. So this is really encouraging, right? So this really means that we can potentially infer, right? We can infer the final sum by just running some partial compute. Okay, so basically these are the sort of the key ideas, right? This is how we do the partial layer compute. So let me try to define what we mean by channel gating in a more formal way. So for each layer, so with channel gating, for the input channels, we first split them. We split them into 2 sets. The first step is called a base pass. Okay. So this is what we use for computing the partial sum. Okay, so per output pixel, we will always run base pass, okay, unconditionally. So this is how we get the score. So once we are done with the partial compute, we get this partial sum, right? And we are going to compare the sum, right? These values with the threshold over here. So through a gate function, and this gate function is going to determine whether this is important or unimportant. So it turns out to be important, and it turns out that we need to run through the rest of the compute. So we'll go through this so-called conditional pass. So this is where we'll use the remaining set of input channels. Of course, the hope here is that we don't need to invoke this conditional pass as often as possible. Right? We only invoke it rarely. So that's how we can get the gain, right? How we can get the savings. Again, we combine these two, right, in the end, right, to form the final output. Okay, so hopefully this makes sense, right? The key idea here is that, again, we are running partial compute, but one thing is we actually need to compare with the threshold. So actually we define the threshold per output channel for each layer. So you can imagine there are actually a lot of a threshold that we have to define, right? So there's no way that we can find this threshold through just doing hyperparameter tuning. That'll be way too much, right? So this is where we have to make sure that these threshold, right, per output channel per layer, this value is learnable. So this is where we actually modified the training graph, right? I'm not going to get into the low level detail of, right, this how the training graph looks like. We actually turn out we can further simplify it a bit, right? But the key thing is that we are able to train our this channel gating network, right? So basically define a new layer type, right? So where we split into two phases, we're able to train this new training gating network end to end in a single pass, and we learn this threshold, this delta automatically. Okay, of course, if you look at the gate function, right, it's actually a step function, right? That one is not differentiable. But we can use it in the forward pass, but for the backward propagation, we need to approximate it, we need to smooth it. So it turns out that if we just use a soft sigmoid, it works well enough. Okay? So we are able to train the whole thing without too much of an issue. Okay, and also the other important thing I want to mention is, some of you may already have the question, right? So how do we pick this base path, right? We pick this small fraction of input channels, which we will always use. So how do we pick? So do we pick the first few or the middle few or the last few? Right? The answer is actually it doesn't really matter at all, right? Since the whole thing is trainable. We can, whether you pick the first few or the middle few, right? The training is going to automatically adjust the weights. So it's not going to matter at all. So this is really where we have a very good flexibility. Okay, so let me show you some quick results. So first on CIFAR-10, this is Rationale 18. We are comparing the baseline, right? So where we have a 5.4% of a test error. With channel gating, we can actually get a 5x reduction in compute without much loss in accuracy. So if we choose a base pass fraction, so this is where we use 1/8, right, of the input channels on the base pass. So this 1/8 will be executed unconditionally. We can go even further, so we can get even higher speed up or compute savings all the way to 8x, right, by losing a little bit more accuracy if we just choose a 1/16, right, for the input fraction. So this is actually pretty encouraging, right? Actually, my student tried to do a little bit more hyperparameter tuning. So it's actually not too hard to regain the further minimize this error without losing efficiency. Okay, and also I want to quickly convince you that indeed we are doing dynamic pruning. So actually we get a different flop reduction, compute reduction for different images. Right? Some of these are easy samples where we are getting higher reduction. Right? Some of the samples indeed we have a slightly lower reduction. But this is the case where we get a 5x reduction on average. Okay, so indeed this is the network, right? This model is responding differently to different input image. Okay, And I also want to point out that this channel gating can be combined with other compression technique as well. Like for example, group convolution. So when we combine it with group convolution, it's actually pretty straightforward. So for each group, right? So for each output group, the corresponding input group will become the base pass, and the rest, right, will become the conditional pass. And we can also do the shuffling, right, like what ShuffleNet is doing. So this actually combines very well. Also, we have tried many other different kind of DNN models, not just ResNet 18, right? Just to make sure that we are not just exploiting the some of the redundancy, right, in a less compressed model. We have also tried to run CG or channel gating on a binarized VGG, okay, and also a different VGG, also MobileNet. Again, we are able to get non-trivial savings in flops without losing too much of accuracy. So this basically indicates that indeed, with channel gating, we are exploiting the input-dependent properties, right? The channel gating is actually complementary to some of the existing compression technique. For example, in MobileNet, we are using group convolution, right? Over here, it's already heavily quantized. So I also want to show you some more results. This is ImageNet. So this is where we have done two-step comparisons. So first, we compare with paper published in Computer Architecture Conference in ISCA. So that they are also doing some dynamic pruning, but they don't really have a learnable method. They don't have a trainable method. If we look at channel gating, we can actually get a huge gain in terms of accuracy and with even higher speed up. We also compare with, in our newspaper, we also compare with quite a few SOTA or state-of-the-art dynamic pruning technique published. So when a year ago, a couple of years ago. So again, channel gating is actually produce better accuracy, right? And also have higher savings. So in terms of flop reduction, so compared to all the existing techniques. Okay, so this is the, right? So, the sort of algorithm part. Hopefully this makes sense so far, right? But some of you may already have the question, right? Since we are doing this fine-grained pruning in the conditional pass, the compute is sort of sparse, right? Actually, the output activation, they are indeed sparse, right? We may have different behavior for different pixels, and also the patterns of the compute may also vary, right, across different output channels and also across different output layers. So what's the difference between channel gating and this traditional, right, more conventional static sparse pruning? So actually the interesting differences here, if you look at channel gating, right, although across the spatial dimension, right, you look at the spatial, the feature map, so we indeed have this sparsity, very sparse. But if you look at the channel dimensions, right, across the input channels, we actually preserve structure. So because when we're going through this gating function, we either gate the entire, right, conditional pass, or we go through the entire conditional pass, right? So we either use them or skip them entirely. So this is actually where we indeed preserve some important structure, which actually helps hardware acceleration. All right, so let me quickly show you some hardware results. Okay. We actually managed to build a very efficient hardware accelerator. This is actually similar to the many popular waste state-of-the-art systolic array design. This, of course, this design works very well for the dense part, right, where we have the unconditional, when we are running the unconditional base pass. We actually also managed to reuse the same hardware to execute the sparse path as well, the conditional path. So again, because we have this, we preserve the structure, right, across the channel dimension. This actually allows us also to make use of this very regular architecture in an efficient way. Of course, the dense part and sparse part are mapped differently, right? But because of the structure that we have, so we are able to map them pretty efficiently. Also, I just want to make a note, since I'm going to talk about us as well, right? In the second part, this whole design is done by 2 PhD students. using hydrosenses or HLS. So they are actually able to design this in a pretty productive way, although there's still some downside with HLS. Right? We are actually, this is one of the important tools that we find really useful. Okay, so we prototype this on, we are able to actually generate some ASIC simulation results. So over here, we are targeting maybe 28 nanometer technology. So we compared it with a standard weight stationary CIFAR array. We call it CGNet. Right? So over here, what we prototype is an 8-bit Rationale 18 model. Compared to the baseline, we are able to get more than actually 2.3x, right, speed up, with close to, this is 1.8x higher energy efficiency. This is where we compare with the baseline, right, without dynamic pruning. So basically, this dynamic pruning itself gives us this much of an improvement. The error overhead is about 20%. If you look at the actual speed up that we got versus the theoretical speed up, so we actually come pretty close. The theoretical speed up is actually about 2.8x. So this is the theoretically best runtime. So this is the purple one is the theoretical performance, right? The best possible case. If you look at the green bar, this is what we actually got. This is actually pretty close. The student actually indeed found some inefficiency in our HLS design. Basically, there are some pipeline bubbles that we are not able to easily squeeze. If you are actually able to fix that, we should be even closer compared to the theoretical speed up. All right, so these are the main darts for channel gating. I also want to briefly talk about precision gating. So you'll find they actually share quite a few similarity. Okay. So this is where we apply pretty much the same idea on quantization. If you look at channel gating, right, we are able to gate the compute by just using a subset of input channels. So with precision gating, this is where we focus on quantization. If you look at neural net quantization in general, right, so you see this trend, where you have to make this trade-off between, again, accuracy and efficiency, right? Of course, we actually want to be able to use low builds, right? We want the build as low as possible, right? Here's an example, right, on ShuffleNet V2, we easily have this trade-off, right? We go down to 5 bits, we are losing accuracy by at least 2%, right? Which is non-trivial. But so really the question is there a way that we can get low bit width execution without losing much of accuracy? So this is where we apply the same idea of dynamic pruning or dynamic gating. So the idea is that we want to run at the low precision. We want to run the network at the low precision or low bit as much as we can. Right? And we only run some of the compute at a higher precision, right? In a few rare cases. So this is pretty much the same with the principle that we use for channel gating, right? So over here, instead of using a subset of input channels, right? So again, we have the sort of base pass and conditional pass. So we are running the base pass with, let's say we use the 8-bit model, we are running the base pass with a 4-bit, right? The upper bits. And then we use it to get the partial sum or partial result. And then we use it to approximate, right, the final sum most of the time, right? And unless in some cases, right, indeed we have to go through this conditional pass. So this is where we have to do the compute in full precision, right? Again, this is decided by a learnable gate, right? So that's why we call it precision gating. So this idea actually turns out to also work very well, right, for dynamic quantization. Just want to show you some results. We actually compare with the baseline with the accuracy. Also, there are a couple of work which also try to do a dynamic quantization, like a dual precision execution. But again, one of the work does not have a learnable or trainable method. The other one is doing it in a much less efficient way. If you look at PG or precision gating, so we are able to get higher accuracy and also a higher sparsity. So higher sparsity means that we are running at the low precision most of the time. This is the bit width, right? So this is going to be fractional. This is going to be a fractional bit width, right? So on average, so we are running the network over here means at 2.1 bit, and we get fairly high accuracy compared to baseline. So look at this is the ImageNet result on ShuffleNet v2. Again, this is a highly compressed model. I just show you some results, right? In the previous slide, the baseline over here is just 59, and turns out that with PG, we can run it at a near 4.8, right? So this is the effective bit width, and we can actually get even higher accuracy. So basically, we get both savings in the right. So in compute, and also we get without losing accuracy. So PG also works. It doesn't just work on ReLU functions. It can also work on different kind of other non-linearity functions. We can also apply it to LSTM. Again, we are able to get pretty good compression, right, in terms of reducing the bit width and without losing much of accuracy. So we actually recently just further applied PG to BNNs, or binarized neural net, which is something I mentioned earlier, right? So one of the problems with BNN is, well, actually, first, BNN is extremely efficient for hardware, right? Since all the activations and all the activation also weights are binary values, right? So there, the map multiply accumulate becomes just XORs and popcon. So those are extremely cheap in hardware, right? So they can be easily implemented on FPGA or ASIC, or even in some of the near memory or in-memory compute devices. But one of the problems with BNNs, so this plot shows that most of the existing BNNs have fairly low accuracy. Actually, in the past, the BNNs are simply not competitive, right, for ImageNet dataset. We recently actually we are developing another called fractional BNN. So this is where we combine a recent BNN model called ReactNet with precision gating. Okay, by doing this, we are able to run the model at every bit with 1.4 bit, okay, and without losing accuracy. So the accuracy is at the same level with MobileNet v2. So we are fairly excited about this result. We already compared it with some of the existing FPGA implementation. This is FPGA 19 paper, where the model is running at 4 bits. So you can see that we get higher accuracy and, of course, much higher throughput, right? Since we are running just binary operations instead of 4-bit operations using the same embedded FPGA device. All right. Okay, so one last slide about this channel gating, also precision gating. I've been mainly on inference, right? So we are able to reduce the execution time, also either flops or the average bit width for inference. So that's obviously important for efficiency. Just want to point out that this technique can be also applied to reduce training time. You are allowed to build a custom training accelerator. So I'm not going to bore you with the math. This is actually just some of the equations that we derived. Right? So this for the back propagation. So it turns out that quite a bit of compute can be also masked away, right? When we are doing this, when we're calculating this input scores, when we rate the compute, we will be able to get quite a bit of compute in the training, in the backward pass as well, not just the forward pass. Actually, some of our collaborators are already starting to explore this direction. They are getting interesting. Some of those will be published soon. Okay, so this is the first part. I just talked about a fairly efficient, right, new DNN layer. So we talk about channel gating, also precision gating. So both of them are highly hardware or accelerator efficient, right? If you think about this gating function, it's just as simple as a comparator, right? So we are really not adding anything else, right? You can sort of think of it as a highly hardware efficient, very lightweight attention mechanism to some extent. So in the second part of my talk, I'm going to talk more about automation, right? So really the hope is that we can actually build this kind of a hardware accelerator in a much more productive way. So I'm going to focus on HeteroCL. It's a new Pruning framework for building this kind of a hardware accelerators. This work recently won the FPGA 19 Best Paper Award. This is a joint work with my student Zhang, Xiaojie, also some of the UCL student, Yuzhe Jie, and with Professor Jason Kang at UCLA. All right, so here's a quick overview of Hydrocell. It's a Python-based programming framework for building hardware accelerators. Okay. So one of the key features of Hydrocell is actually decouples the algorithm spec from different customization techniques. Okay, I'm gonna talk about this pretty soon. So this actually allows us to get high productivity, also good performance and portability across different hardware accelerators. For now, we have been mainly focusing on FPGA. So we are also adding backend for in-memory compute PIM devices. And later on, we'll also look at ASIC as well. Hydrocell is actually already open source. Most of the features that I'm going to mention later on, they're already available in the public repo. All right, so just want to quickly, to help you understand what exactly is this hardware customization techniques, right? So if you think about the essence of hardware acceleration, right? So it's really about running many compute units in parallel, right? So this is where we can exploit parallelism by using techniques like unrolling or pipelining, right? We call this as compute customization. And in many cases, we actually want to run even more things, right? Even more compute units in parallel. So this is where we can make trade-off between precision and efficiency by leveraging some of the customer data types like low bit with integer or fixed point types. Right? Of course, the challenge is, we have to be able to feed data, right, to these many parallel units so that they are as busy as possible. So this is where we have to, in many cases, create a customized memory hierarchy, right, instead of relying on the general purpose one. Right? So this is what we call memory customization. So if you look at these many different customization techniques, in fact, they actually don't just work in isolation, right? So there's some pretty in between different customization techniques. So one of probably the most important and most interesting aspect is how the data get placed, right, and also moved between the this customized storage and also the compute units. So we also have we also provide a programming interface to capture this kind of interdependent or data placement between these different customized units. All right, so actually I mentioned HRS, right? Hopefully some of you are familiar with HRS. If you look at HRS or hallucinations, they are actually able to capture many of these important customization techniques. So if you look at the code on the right-hand side here, some of these code are used for customized compute. Some of them are like this fixed point type or custom data type, right? Also there's line buffer and window buffer for custom memory. But the problem is that most of these, you look at the code, right? So the algorithm is actually entangled with different customization techniques. So the code becomes no longer, readable or portable, right? If you are actually an HRS expert, you might be able to quickly understand, right, and figure out what exactly is going on. But if you're not, it's going to be hard for you to actually realize that this is just doing a simple 2D convolution, right? The key kernel in deep learning. So the goal here is that we actually really want to make it cleaner, right? So actually this challenge is not new, right? For if you look at CPU and GPU computing, domain-specific computing, right? So people have been also dealing with this challenge, right? Some of the early work, like Halide and TVM, they actually propose to decouple the loop population and temporal schedule, right, from the algorithm spec. But they don't really focus much on the custom hardware. But that's where they usually don't touch on the memory aspect, custom memory aspect, and also data type. With Hydrocell, what we want to do is we actually want to fully decouple the important hardware customizations from the algorithm specification. And also, we really want to capture the interdependence between them as well. Okay, so hopefully this gives you a good overview of what we are trying to do with Hydrocell. So let me show you some example. So here's a very, again, this is a very simple example. This is a 2D convolution. Right? Over here with Hydrocell, we can do declarative programming or imperative programming. So I'm showing declarative code over here. So with a lambda function and two reduction axes, we are reusing the TVM syntax for the declarative code. So this basically corresponds to a 4-level loop nest. The nice thing about HydroCell is we have a separate code section where we decouple these customizations, right? So we can do unroll. To unroll the inner loops, we provide a primitive called quantize. So this is where we can quantize a floating point value into fixed point types or local with integer. We also provide a new primitive like reuse set. So this is where we can infer on-chip data reuse buffer like line buffers or window buffers, right? Also, in addition to these primitives, so we also provide something called hetero flow. So this is where we capture the data placement, data movement, right? So I'm not going to bore you with the details of the code. I'm going to quickly mention we actually introduced something called .2. So this .2 primitive is pretty useful in the sense that we can decouple the data placement from the algorithm specification. So over here, we are saying that, again, this is a algorithm where we are doing 2 COM kernels back to back. This is 1D COM kernels. So with .2, we can specify that we offload the data, the image weight, to the target accelerator. And then it's automatic. And then the tool will also automatically infer these communication channels, like by default streaming DMA, right? So where we don't need to bother the user to write tedious driver code. Nice thing about 2 is the communication or the data movement between the sub-modules within the same accelerator. Right? So over here, we are using a third.2. This is basically that we want to do data streaming between 2 COM modules, from COM1 to COM2. Right? And even better, so we can actually go, we can do the decoupled data placement in the even finer scale, finer granularity. So if we zoom into this 1D convolution kernel, right? Over here, we're doing 1D convolution, right? So fairly clean, right? Very simple 2 lines. But many different architecture choices, right? So let's say we want to implement the weight station design described in this classic paper by H.T. Kang, right? We first want to duplicate the MAC units to a few PEs, right? This can be done by a simple unroll primitive. We need to do a broadcast, right? So with the input X. So this can be done by .2, one-to-many .2. And we also need to do this systolic communication, right? By moving Y, right? So across these PEs. So again, we can do .2. We can do a cascaded .2. So the beauty here is that again, the algorithm code is the same, right? But we cleanly captured the hardware structure, right? Using this set of primitives. So this is where we can easily implement a weight station design. All right. So this is the sort of menu of the customization primitives that we provide right now. I just mentioned some of those, right? There are more. And actually, we also provide this sort of macros. So this is where it's basically a combination of many primitives, right? Micro primitives. So right now we can quickly generate highly efficient architecture for like stencil code and also systolic, right? Systolic algorithm. Okay, so this is the compiler, the compilation flow for HydroCell. So right now we are relying on HOS to target the either embedded FPGA or cloud FPGAs. We can also generate efficient code for CPU. We are actually building new backend, like I mentioned, for PIMs and also later on ASICs. So here are some results. Just want to show that with HydroCell, we are not limited to just DNN or deep learning kernels. We can actually handle a fairly wide range of different kernels. Since HydroCell also support in-pair programming, we can do image stencil kernels. We can generate pretty high performance system arrays for either dense linear algebra or the deep learning kernels. Okay, we can get pretty good speed up, right? So this is on AWS F1 FPGA compared to optimized CPU libraries. And in general, can handle other applications like, not just deep learning, and we can handle like KNNs or K-means as well. We also evaluate Smith-Waterman. This is from genomics. Okay, so these are the kernels. One interesting case study I want to briefly mention is at Cornell, I teach senior graduate level class. So where students get to learn hardware acceleration and also HOS. So one of the interesting labs that we did last time in the recent offering is that we asked the student to implement a fairly simple BNN, or binarized neural network. We want the student to get speed up, right, on embedded FPGA, this is Zhang FPGA from Xilinx. So the student who get higher speed up over ARM CPU will get higher scores, right? So they're actually motivated to get good performance. The good thing is most students actually manage to get some speed up, right? Some less than around 10x or slightly less than 10x. So most of them get good speed up. But the bad news is that with just the current HRS tools, so only 2 students, right, out of a class of 30 plus bright students, only 2 of them figure out the best design. So where they get more than 50x speed up. So we actually look at their code. It turns out that indeed, this is their implementation of BNN. So it's non-trivial to get the good speed up, right? So like I mentioned, they actually need to implement quite a few of different kind of a customization technique in HRS, and they need to be combined in an efficient way, right? So this is certainly a non-trivial task. So later on, some students, right, they actually had the audacity to try out our new HydroCL proving framework. So this is the project they proposed for their final course project. So they actually tried to re-implement the whole BNN using HydroCL. The cool thing is they actually managed to develop the entire BNN. Again, this is a fairly simple one, so with just 3 or 4 layers, but they are able to get a pretty good speed up with HydroCL within just a few days. Of course, this is not apples to apples comparison anymore, right? Since the student already sort of familiar with, they're already familiar with the BNN code. But it's still good to know that they were able to use the new Pruning model and then get very good performance out of the box, pretty much. All right, so one more case study. So this is a more complex BNN, right, which we recently implemented with HydroCL. This is done by an undergrad student. I just mentioned this new model called ReactNet, right? So that student is actually able to design the whole thing in HydroCL. The reason that we are focusing on CIFAR-10 is, I already mentioned the reason, right? So most of the existing FPGA or ASIC BNN accelerators, they focus on CIFAR-10 since the previous BNN models are not that efficient. They cannot provide good accuracy on ImageNet. So that's why we are making this comparison. So again, we are able to fairly quickly implement a new BNN model using HydroCL. So this is on FPGA. We are able to get a much higher throughput compared to the prior work. Since this is done by an undergrad student, I'm pretty happy with the result. Okay, so this is the last slide on HydroCL. Like I mentioned, this is an open source framework. Some of our industry sponsors are already exploring this tool. Some of them are already using them. We have a public website with quite a few useful examples. If you're interested, please do check it out. Just to wrap up, right? I mentioned, right? So we are exploring this intersection between efficient ML and hardware acceleration, right? So for this talk, I only talk about 2 projects, right? So one is dynamic gating, the other one is HydroCL. So this slide shows sort of a more global picture of what's going on in my research group. So again, we are trying to develop a full stack approach where we are trying to do this hardware algorithm co-design, right? I'll be very happy to talk more offline, right, about some of our efforts more on the compiler and hardware side, right? So where we are also trying to develop some of the custom accelerators for other kind of sparse machine learning models. And many of the projects are open source, so you can check out this link, right, to find our other projects. So in summary, I really think that the co-design, the algorithm hardware co-design will give us the highest efficiency, just like what we have shown, right, with channel gating and precision gating. Okay, so this is my final slide. I just want to give credits to the sponsors who are funding our work. Right? Actually, we are part of the Jump Center, Chris Center, that is part of the one of the 6 Jump Centers. Samsung is one of the sponsors. Right? So thanks for your support. Also, credit students So this is actually a picture taken last year at this beautiful Cayuga Lake in Ithaca. For good reason, so I cannot update this picture, right? So this is taken a year ago. Hopefully, this pandemic will be going away, hopefully soon. So we'll get to take a new picture in the near future. All right, so thanks for your kind attention, right? Again, I hope you are doing as well as possible.